Okay, so now we're going to talk about equilibrium. And equilibrium is based on kinetics because we're talking about reversible reactions. So think about the reactants turning into the products around the hill and the products turn back into the reactants, and they can go either way. And we've run into these before in the past. When we were talking about, the one that's coming to my mind is when we did the hydrate lab. We took that blue stuff, we added heat, it turned white because we drove off the water. That was the forward reaction. But when we added the water back in by putting in a few drops, boom, it turned back to blue. Okay? That was an example of a reversible reaction, something that we can make go backwards to what we originally started with. And so we're going to start talking about reversible reactions, but we're going to have to talk about what's called dynamic equilibrium. And in dynamic equilibrium, that is the point at which the rate, that's why we're talking about kinetics, of the forward reaction equals the rate of the reverse. So you've got your little hill, and it doesn't matter what kind of a hill it is. You got reactants turning into products, and you have products turning back into reactants. And so there's kind of like it's almost like a vicious circle. One goes this way, and one goes that way. That's what equilibrium is, the rate at which it happens. As this one turns into this one, and the products turn back into the reactants turn into products turn into reactants, the rate at which that happens, the speed, if you want, is the same at equilibrium. The number of molecules that change. So if I had 5 reactants turn into 5 products, I would have 5 products turn back into 5 reactants. That's what happens. It doesn't mean it stops. What it means is that the reaction is continuing to go, but you're not losing or gaining any amount of reactants or products. And it also doesn't mean that the concentrations are equal, the amounts that you have are equal. I might have 100 of these and 10,000 of those. But the net amounts don't change. If I have 5 go one way and 5 go back the other way, I still have 100 and I still have 10,000. That's what equilibrium is. Chemical equilibrium is when the concentration of the products and the concentration of the reactants remain the same. They don't change. The net amounts don't change, but the rates at which they change are the same. Every reversible reaction hits an equilibrium state, and that's referred to as a Keq. They use this thing called an equilibrium constant, and it's called a Keq. If you take AP Chem, you're going to be doing it a lot. Equilibrium means it's balanced. Okay, the rate of the forward reaction equals the rate of the reverse reaction. Okay, the time in which they go. And so there's no net change in the amount that you have. The way you calculate an equilibrium constant, it tells you how much of the reaction has proceeded to completion. In other words, basically where you are. Do you have 10,000 of one and 1 of the other? It's hard to tell until you have this value. So the equilibrium expression, based on any reaction, no matter how it's written, is always written as the product concentration. That's what those little brackets mean. So they mean molarity of C raised to its coefficient times the molarity of D raised to its coefficient, right here, divided by the molarity of A raised to its coefficient multiplied times the molarity of B raised to its coefficient. Or a lot of times people write it as products over reactants, meaning the coefficients have to be included, and the products are all multiplied, and the reactants are all multiplied, but together, it's products divided by reactants. And it means concentration. The little brackets mean concentration and molarity. So, if Keq is bigger than 1, a lot bigger than 1, and you're going to see some really big numbers. I mean, potentially, in AP Chem, we see them like 10 to the 23rd, 10 to the 40th, that kind of thing. If it is significantly greater than 1, what that means is there is more product. Remember, Keq is the concentration of the products over the concentration of the reactants. If it's much greater than 1, that means this number on top is very big and the number on the bottom is very small. Big number divided by small number, boom, bigger than 1. And the products are referred to as being favored. And equilibrium lies to the right. In other words, on my little hill, all right, I've got my reactants and I've got my products. This might be 1 and that might be 10,000. Products are favored. There's a lot more products than there are reactants. If Keq is significantly less than 1, what that means is the number on top is very small and the number on the bottom is very large. And that's referred to as the reactants are favored. And the equilibrium is predominantly this way. This might be 10,000 and this one might be 1. It doesn't really start. It just kind of hangs out. Okay, there are just basically more reactants present than products. The reactants are favored. If the Keq is about 1, that means you have about an equal amount of reactants and products. But you don't see that very often. Most often it's significantly different from 1. A homogeneous equilibrium is where you have everything as one state of matter, either aqueous or gaseous. If you have solids and liquids involved in a heterogeneous equilibrium, Keq only uses gases and aqueous. No solids, no liquids. So if you see them, you just kind of ignore them. They're not part of the reaction. They're not part of the equilibrium. And the reason why, I'll erase that. The reason why is because the amount of solids and liquids doesn't change very much at equilibrium. Equilibrium is a very fine balance. It really is. And so they don't change enough because they're such high concentrations to begin with. They don't change enough to make it even worth measuring. And so they just leave them out of the Keq. So I'm going to have you guys practice writing the equilibrium expressions for the following reactions. Remember, Keq is the concentration of the products over the concentration of the reactants. Only for gases and aqueous. So if I look at this, I see everything's a gas. So if I was to write Keq, I would take my products. Let's remember products are over here, reactants are over there. I'll put NH3 inside brackets, and I'm going to square it because it has a coefficient of 2. On the bottom, I'm going to put my reactants, N2 to the first power, which you can write if you want, or you don't have to because it has a coefficient of 1, multiplied. I know it's added here, but in the Keq it's multiplied hydrogen raised to the third power because it has a coefficient of 3. That's your equilibrium expression. It's the setup, essentially, is what it is. Okay? Go ahead and let's do this one. Keq, remember reactants, products, is HI, is my product. I need to square it. I notice it's a gas divided by my reactant, hydrogen, which is also a gas, but I'm not going to include the iodine because it is a solid. That's my Keq expression. You have to watch for that. It's tricky. No solids, no liquids. If you want, essentially you would put in 1 for those. You don't even include them. Okay? So let's go ahead and do this one. Keq is products over reactants. So water raised to the 6th power multiplied times NO2 raised to the 4th power. I know it says plus, but in the Keq they're multiplied. Over, everything's a gas, NH3 raised to the 4th power, and oxygen raised to the 7th power. Okay, so that's your Keq expression. It's always products over reactants raised to their coefficients for gases and aqueous, no solids. Okay, now we're going to start probably doing some calculation with that. Using the Keq expression, I want you to calculate the value. Now remember, Keq is products, NH3, squared, because it has a coefficient, over N2 to the 1st power multiplied times H2 cubed. That's the expression. That's the setup. Now I'm just going to plug in the numbers. Keq is, the ammonia number goes on top, NH3, so I got 3 squared, over, on the bottom I have 1 to the 1st power, multiplied by 2 to the 3rd power. Now I want you to make sure, if you're not very good at doing this on your calculator, I'd like you guys to take the time to actually write this out. I know we are lazy human beings, but 3 squared is 9. And then to do 2, you want to use the little button that looks like this. It's 2 that to the 3rd power on a graphing calculator. I don't remember what it looks like on anything else. That would be 8. And then divide it out. Because you're going to start to get numbers that don't really make a whole lot of sense, or they tend to be very large or very small. So you might as well just do it properly and make sure you get the math right. Now the other cool thing about Keq is it has no units. Yay! No letters need to be written after Keq. Even though this is molarity, and this is molarity, what ends up happening is the molarity units end up being very strange. And so they just say, you know what, screw it. And it changes every time. So we're not going to do it. We're just not going to do it. Okay? Now, I'm going to use the Keq expression again. Remember, the expression was products over reactants. And it doesn't matter the order you write them in on the bottom. Okay, as long as you remember to multiply them and cube the hydrogen. Kq is 25. Now we're going to find the missing value for the nitrogen. So I'm going to put in 25 for Keq. And on the ammonia, I'm going to put in 4, and it needs to be squared, over 2, which needs to be cubed, and then the missing one, we're going to call it x. Now, I know you guys struggle with this. Okay, I know you do. So I'm going to put that over 1, and I'm going to solve the algebra. I'm going to go kind of slow. So I got 25 over 1 equals, and then 4 squared is 16 over 8 times x. Okay, a couple of ways to handle this. Personally, what I would do is I would cross multiply, and I would get 16 equals 25 times 8, it should be 200, right? 200x, x is therefore 0.08, and then that, because you were solving for a concentration, that does have a unit. K doesn't, but that does. Okay, and all I did was solve for it, and if you want, a good thing to do would maybe plug it back in and see if you get 25 when you plug it back in. But it should have a unit because you're solving for a thing in brackets. That means molarity. Okay, now we're going to try one more problem, a little bit harder. Okay, Kq, still the same setup based on the products over the reactants. And all you need to do is plug and chug, but it is a little bit trickier on this one. Keq is 0.0055 equals, well, the ammonia, we don't know what that is, so I'm going to call that x, but don't forget, it needs to be squared. Okay? We're solving for x, but it needs to be squared in this expression, the setup. We're going to put N2 on the bottom, and hydrogen cubed. Okay? Put this over 1, and so you're going to get 0.0055 over 1 equals x squared over 8 times 3 is 24. Okay. Cross multiply. So 0.0055 times 24 is 0.132 equals x squared. Take the square root of both sides, and you get 0.363. And again, it's going to have a unit of molarity because you're solving for a bracket. Okay. Another thing you can do is plug that in and see if it works. It should round. I mean, there's rounding issues or whatever, but it should be pretty close.